работает. Okay, so at the previous lecture, we began to discuss the quantum analog of a higher measure on compact groups. Actually, we only discussed some motivations which lead to this notion. So let's recall these motivations. So if G is a compact topological group and mu is a Radon measure, positive Radon measure on G, we defined the left and right translates of mu as follows. If X is an element of G, then Lx of mu is a measure given, and the right translate of mu is defined as follows. And we say that mu is left invariant if Lx mu equals mu for every element x in G. And similarly, we define the right invariance. We say that mu is the right invariant if the right translate of mu equals mu for every element in G. And there is a fundamental result due to Haar, von Neumann, and Andre Weil that for every compact topological group, and actually for every locally compact topological group, there exists a left invariant Radon measure and a right invariant Radon measure. Actually, they are essentially unique. If we have two left invariant measures, then they are the same up to a constant, up to a multiplicative constant. And the same is true for any two right invariant measures. In the general case, a left invariant measure is not necessarily right invariant, but for compact groups, this is true. This is a result due to von Neumann. So every left invariant measure on a compact group is right invariant, and the other way around. So when we speak about compact groups, so let's recall that in general, a Radon measure is assumed to be finite on compact sets. So if G is compact, then mu is finite. And it is reasonable to normalize mu in such a way that mu of G is 1. So we say that mu is normalized if mu of G is 1. Clearly, we can always, if we have an arbitrary positive Radon measure, we can always normalize it by dividing mu by this number. And in the case of compact groups, the main result about the invariant measures can be stated as follows. So this is a special case of a theorem which was stated at the previous lecture. If G is compact, if G is a compact topological group, then there is a normalized left and right invariant positive Radon measure on G, which is not identically 0. And second, it is unique in the following strong sense. If nu is a positive Radon measure on G, and if nu is left or right invariant, then nu equals mu. Nu is normalized. and mu is left or right invariant, then nu equals mu. And this mu is called the Haar measure. Mu is the normalized Haar measure. It is unique. So our goal will be to extend this result to compact quantum groups. And let's also recall a result which was obtained at the very end of the lecture, which characterizes such measures in terms of functionals on the algebra of continuous functions. So we let A denote the algebra of continuous functions on G. So we know that the tensor product of A by itself is nothing but the algebra of continuous functions on G cross G. The standard co-multiplication on this algebra acts by the following formula. It is dual to the multiplication on G. Every measure, mu, generates a functional h on A, given by integration with respect to mu. And we also introduced, for convenience, we introduced the unit map, eta, which acts from the complex numbers to A, and is uniquely determined by the following simple formula. So it takes the identity in the base field to the identity in our algebra. And we observed that mu is left invariant if and only if H satisfies the following condition. 1 tensor H composed with delta equals eta H. So this is a map from A to itself. 1 tensor H is the slice map, which is well defined on the spatial tensor product of A by itself. So this formula is precisely equivalent to the left invariance of mu. And similarly, we observed that mu is right invariant, if and only if H tensor 1 composed with delta equals eta H. And this observation naturally leads to the following definition. So let's now take an arbitrary compact quantum group, not necessarily commutative, A and delta. This is a compact quantum group. And suppose that H is a positive linear functional on A. So we simply take these two properties as the definition of left and right invariance. We say that H is left invariant, respectively right invariant, if we have this property, 1 tensor H composed with delta equals eta H, and respectively H tensor 1 composed with delta equals eta H. So we see that in the case where A is commutative, in the case where A is the algebra of continuous functions on a compact topological group, in this case H is a bounded linear functional on C of G. So by the Riesz representation theorem, it corresponds bijectively to a positive Radon measure. And this property is indeed equivalent to the left invariance of the respective measure. So at least this definition is quite reasonable. The invariance property of a linear functional can also be conveniently stated in terms of convolutions. So let's give the respective definition. Suppose we have two linear functionals, two continuous linear functionals on our algebra A. So far, still we assume that A is a compact quantum group. And we define the convolution of f and g to be a linear functional on A, defined like this. It is denoted like this, f star g. And it is defined by the following inequality. So first we apply delta. It takes A to A tensor A. And then we apply this functional f tensor g. And so we already know that this is a well-defined bounded linear functional on the dual of the tensor product, on the dual of A tensor A. So the resulting map is indeed a bounded linear functional on A, and we say that this is the convolution of f and g. By the way, the Russian for convolution is svertka. A special case of this construction is the convolution of measures. Convolution of measures. If G is a compact group, if G is a compact topological group, then we denote by M of G the space of all complex Radon measures, on G. And the Riesz representation theorem tells us that this space is canonically isomorphic to the dual of C of G. More exactly, if we have a measure, a complex Radon measure mu on G, then the respective functional f mu is just the integration with respect to mu. And this is a one-to-one correspondence. So if we now apply our definition to this special case, we see that if we have two complex Radon measures, mu and nu, then their convolution is uniquely determined by the following formula. For every continuous function f on G, the integral of f with respect to this measure is just the integral of f of xy d mu of x d nu of y. For every continuous function f. Well, this is non-trivial. The Riesz representation theorem tells us that this map is an isometric isomorphism. But the proof of this fact is non-trivial. What is indeed non-trivial here is to show that this map is surjective. And this is non-trivial. The main reason why it is non-trivial is that we don't have an explicit construction for the inverse map. So any proof of the Riesz representation theorem involves an explicit procedure of showing that this map is surjective. But there is no explicit formula for the inverse map. That's the point. Okay, so let's now observe the following. Actually, this is an exercise for you, that if A is a compact quantum group, then A star equipped with the convolution operation becomes a Banach algebra. Is a Banach algebra under convolution. in particular, the associativity of the associativity of the convolution follows from the co-associativity of the co-multiplication on A. And also, let's also observe that the convolution preserves positivity. You have two positive functionals on A. Then, first of all, the tensor product is a positive functional on A tensor A. And if we compose this with delta, we get that the convolution of f and g is also positive. And moreover, if both f and g are states of A, then their tensor product, oh sorry, this is, of course, this is not equivalence, this is just an implication. If they are positive, then their tensor product is positive. And if they are states, then their tensor product is also a state. This is more or less immediate because let's recall that a positive functional is a state. A positive functional on a unital sister algebra is a state, if and only if it preserves the identity. So if they preserve the identity, then this also preserves the identity because the co-multiplication is a unital homomorphism. So this is also a state, and this implies, just because delta preserves the identity, this implies that f convolved with g is also a state on A. This is also a state. Okay, now we are ready to prove the following useful characterization of left and right invariant functionals. Suppose that A is a compact quantum group, and H is a positive linear functional on A. Then the following conditions are equivalent. Condition 1, H is left invariant, respectively right invariant. Condition 2, for every bounded linear functional omega on A, we have the following identity. Omega convolved with H is omega of 1 times H. So this is equivalent to the left invariance, and respectively, H omega equals omega of 1 times H. This is equivalent to the right invariance of H. And part 3, the same property holds for all positive functionals. For all positive linear functionals on A, we have property 2. The proof involves the following lemma. And the proof of the lemma is an exercise for you. The lemma states that if A is an arbitrary sister algebra, then for every non-zero element A of A, there exists a state, omega on A, such that omega of A is non-zero. Well, you probably remember that some time ago we proved this result under the assumption that A is normal. When we proved the second Gliffand-Nymrock theorem, we proved this lemma in the special case where A is normal. But actually, by decomposing A into the real and the imaginary part, we can easily extend this result to an arbitrary non-zero element. So, but this is a simple exercise for you. Well, let's now prove our proposition. So let's look at both parts of this equality. omega convolved with h is omega tensor h delta. And this can be written as the following composition: omega 1 tensor h and delta. And on the other hand, omega evaluated at the identity times h can be written as follows: omega eta h. And by comparing these two expressions, we conclude that 1 implies 2. If h is left invariant, then this functional and this functional are the same. And so, of course, they are the same after applying omega. So 1 implies 2. 2 implies 3, this is clear. 3 is just a special case of 2. And to prove that 3 implies 1, we use our lemma. So if these two numbers are the same for every positive linear functional, we see that for every positive omega, omega composed with 1 tensor h delta minus eta h is 0. This is just another form of this equality. But since we already know from the lemma that states separate the points of our algebra, we conclude that since this is true for every omega, then the expression in brackets is necessarily 0. So our lemma implies that 1 tensor h delta minus eta h is 0, which means precisely that h is left invariant. So this completes the proof. Okay, we are now ready to prove the following fundamental result due to Voronovich. So suppose that we have a compact quantum group, A delta. Then, first of all, I claim that there exists a state, H on A, such that H is left invariant and right invariant. And second, this state is unique in the following sense. If F is another state on A, and F is either left invariant or right invariant, then F equals H. So in particular, we see that such a state H is unique. And we say that H is the Haar state. On A. The proof of this result is naturally divided into two parts. The conceptual part and the calculational part. So let's start with the conceptual part. Lemma 1. I claim that for every state omega on A, there exists another state H on A, such that omega H equals H omega equals H. Well, this is a weak form of our theorem. So what we want to find a state H which satisfies this condition for every omega. So let's look once again at our proposition. So if this property holds, if both properties hold for every omega, then this means exactly that H is left and right invariant. But at this point, we state that the existence of such an H for a unique omega. So for every omega, there is an H. The proof is more or less constructive. Namely, for every natural number n, let's introduce the following functional Hn, given by the following formula: 1 over n, omega plus omega, omega plus, and so on. So we have n summands, and the nth summand is omega to the power n. So clearly Hn is a state, because we know that the convolution of two the convolution of two states is a state. Sorry, the convolution of two states is a state. So every summand here is a state. So the sum is a positive functional, and after dividing by n, we get a state, a functional which preserves the identity. So it is a state. Now let's observe that the set of all states is a closed subset of the weakly star closed subset of the unit ball of the dual space of A. So if we equip the set of states with the weak star topology, then this topological space is compact, because the unit ball is the weakly star compact. So as a result, this sequence Hn has a convergent subnet. There is a subnet Hn of lambda, which converges to H, where H is a suitable state on A. I don't claim that this is always a subsequence. If A is separable, then S of A is even metrizable. And in this case, the space is sequentially compact, so we can choose this convergent subsequence. In the general case, we have a convergent subnet. And I claim that this is exactly what we're looking for. Well, indeed, if we explicitly calculate the convolution of Hn and omega, we find that that omega Hn minus Hn, minus is it correct? Yeah, omega Hn minus Hn, or equivalently Hn omega minus omega. So what is this? So almost all summands cancel, and the result looks as follows. This is 1 over n, omega to the power n plus 1 minus omega. I hope this is correct. Yeah. And this is bounded. Omega is a state, so this is bounded by 2. So as a result, if we substitute here n of lambda, we take our subnet and let lambda go to infinity, we deduce that omega h equals h omega equals h. And this completes the proof of lemma 1. The calculational part of the proof of our theorem is hidden in lemma 2. Lemma 2. This lemma states that if we have two, if H is a state, first of all, if H is a state on A, and if we have two positive functionals, nu and omega on A, which are positive and such that nu is dominated by omega in the sense that we have this inequality. And I claim that if omega satisfies the following condition, which appears in the definition of left invariance, then nu satisfies the same property. Nu h equals h nu equals nu of 1 h. So before proving this lemma, let's understand how this lemma implies our result. So proof of theorem modulo lemma 2. Again, this is the conceptual part of the proof. So for every positive linear functional on A, consider the following set, let's denote it by k omega. So this is the set of all states H on A, satisfying this condition. Omega H equals H omega equals omega of 1 H. So what can we say about this set? First of all, a simple exercise hidden in the proof is that the multiplication on A star, that is the convolution, is separately weakly star continuous. The convolution on A star is separately weakly star continuous. That is, it is weakly star continuous in each variable. This is more or less immediate from the definition of the convolution. And this implies that k omega is closed in S of A. But S of A is a compact space by the Banach-Loglu theorem, so we conclude that k omega is compact for the weak star topology. If we now look at lemma 1, we see that k omega is non-empty. Well, indeed, by lemma 1, for every omega, there is an H satisfying this condition. So lemma 1 means precisely that k omega is non-empty. So as a result, we see that we have a family of non-empty compact sets. And what we want to do, we want to show that there exists an H satisfying this condition for every omega. So in other words, we want to prove that the intersection of all these sets is non-empty. But they are compact, and by the compactness property, it suffices to show that this family satisfies the finite intersection property. That is, all finite intersections are non-empty. But for every finite family of positive functionals, the intersection of k omega I from 1 to n contains k corresponding to omega 1 plus omega n. Because this sum dominates every omega I, and by lemma 2, if this functional H satisfies this condition where omega is this finite sum, then the same condition is satisfied for every summand in this sum. So it belongs to this intersection. This is true by lemma 2. But this is non-empty. So this intersection is also non-empty. And this is true for every finite family. So now by compactness, we conclude that the intersection of all the family k omega is non-empty. So now if H belongs to this intersection, we see that H is left and right invariant. Because this property holds now for every omega, for every positive functional omega. And our previous proposition states that, this proposition states that H is left and right invariant. So why is it unique? This is very easy. So the uniqueness of H, if F is another state, if F is a state on A, suppose that F is left invariant. Then F equals H convolved with F by the left invariance of F. But H is right invariant. So by the right invariance of H, this is equal to H. And that's it. So this completes the proof modulo lemma 2. So let's now discuss lemma 2. This is the calculational part of the proof. The proof involves two equalities, this one and this one. So we'll prove only one of them because the proofs for both parts are very similar to each other. So we'll show that nu convolved with H equals nu of 1 H. We'll prove this equality. We also may assume that omega is a state. That omega is a state, because otherwise we simply multiply everything by a suitable constant. So let's introduce some notation. For every element B in A, let C of B, or simply C, denote the following element: 1 tensor H applied to delta of B. So this is an element A. We have the following auxiliary result. Let's call it sublemma 1. Sublemma 1 is the following identity: 1 tensor FH applied to B equals 1 tensor F applied to C, where C is given by this formula. The proof is quite straightforward, so this is an exercise for you. The proof involves the co-associativity of delta. Co-associativity of delta. Okay, now sublemma 2. Sublemma 2. So what we are going to do is to reduce this equality, which we want to prove, to another property. So this equality holds if and only if for every pair of elements A and B in A, we have the following inclusion: A tensor 1 multiplied by delta C minus C tensor 1 belongs to the kernel of the following functional H tensor nu, where C is of course is C of B. C is given by this formula. Well, indeed, why is it so? Well, our equality, omega h equals, nu h equals nu of 1h is equivalent to the following one. This is equivalent to h tensor omega, h tensor nu h equals nu of 1 h tensor h. So we simply tensor everything by h on the left. Clearly, these two equalities are equivalent. So both parts of this equality are bounded linear functionals on A tensor A. And we know that A tensor A contains two useful dense subspaces, which appear in the definition of a compact quantum group. So it suffices to show that these functionals are the same on the following subspace, A tensor 1 delta of A contained in A tensor A. So this is a dense subspace. Well, formally, this definition of a compact quantum group involves another, slightly different subspace obtained from this by interchanging A tensor 1 and delta A. But by applying involution, we see that this subspace goes to this one. So the density of this one is equivalent to the density of this one. They are simply related by the involution. So for the proof, it is more convenient to use this subspace. Okay, let's now calculate both parts on elements from here. We start with the first one, nu of 1, h tensor h applied to A tensor 1 delta B. So what is this? This can be written as follows, nu of 1 h. So h tensor h is the composition of h and the slice map 1 tensor h. So, and we apply this to A tensor 1 delta B. 1 tensor h is easily seen to be a morphism of left A modules. So the left multiplication by A by A tensor 1 here, can be replaced by the following. This is nu of 1 h applied to A times 1 tensor h applied to delta B. This is because 1 tensor h is a left A module morphism, a left A module homomorphism. So what is this? This is our element C. This is precisely C. So this is nu of 1 h applied to AC. And for convenience, we write this element as follows: h tensor nu applied to AC tensor 1. Okay, so this is what we get after evaluating the right-hand side of this equality at this element. So finite sums of such elements are dense in here. Let's now evaluate the left-hand side of our equality. H tensor nu h applied to the same element, A tensor 1 delta B. So what's this? Again, we decompose this as H and one tensor nu H applied to the same element, A tensor 1 delta B. And again, we use the simple fact that this map is a left A-module homomorphism. So this is H applied to A times 1 tensor nu H applied to delta B. And now we use sublemma 1. Sublemma 1, which implies that this element is nothing but one tensor nu applied to delta C. So by sublemma 1, this is H applied to A times one tensor nu applied to delta C. Okay, now we do a kind of an opposite procedure. So we again use the fact that one tensor nu is a left A-module homomorphism. And so this is H composed with one tensor nu and applied to A, one tensor nu applied to A tensor 1 times delta C. Or equivalently, simply H tensor nu applied to A tensor 1 delta C. Okay. So now, if we now compare this and this, we see that our equality nu H equals nu of 1H holds if and only if these two numbers are the same. That is, if and only if H tensor nu applied to their difference, and their difference is A tensor 1 delta C minus AC tensor 1 is 0. Or in other words, this is H tensor nu applied to A tensor 1 times delta C minus C tensor 1. So this means precisely that this element sits in the kernel of H tensor nu, exactly as stated in sublemma 2. Is it correct? A tensor 1, yes. Delta C minus C tensor 1. Okay. So this completes the proof of sublemma 2. So sublemma 2 reduces what we want to prove to another statement, to this inclusion. The next step is to reduce this inclusion to another inclusion. So first of all, we introduce some notation. Let's introduce the following subspace, AL H tensor nu, which consists of those elements U in the tensor product, such that H tensor nu applied to U star U is 0. Well, we have already met such subspaces when we discussed the GNS construction. So this functional is positive. And in fact, we already know that this subspace consists of those elements U, such that this functional applied to VU is 0 for every V in A tensor A. Let's recall that this equality follows from the Cauchy-Bunyakovsky-Schwarz inequality applied to this positive functional. Sublemma 3. If for every element B in A, the element delta C minus C tensor 1 sits in the kernel of H tensor omega, then we have this property. Let's denote it by 1. Then for every A and B, we have this inclusion. So in other words, to prove this inclusion, it suffices to show this. Well, why is it so? Well, actually, this is very easy, because oh, sorry, this is not correct. Not in the kernel of H tensor omega, but rather in L. Sorry about that. In this subspace L corresponding to H tensor omega. Well, this is correct. Well, why is it so? Well, indeed, we know that nu is less than or equal to omega by assumption. This readily implies that L H tensor omega is contained in L H tensor nu. So if this is true, this element is positive, so if this vanishes for omega, then the same vanishes for nu. But on the other hand, this is contained in the kernel of H tensor nu, because we may substitute the identity for V here. So this is contained in this kernel. And finally, let's recall that this subspace is not just a subspace, but this is a left ideal. This is a left ideal of A tensor A. So if this element belongs to this subspace, to this ideal, then after we multiply it by A tensor 1, this product will also belong to this subspace, and by this chain of conclusions, it sits in the kernel of H tensor nu. So we have property 1. Okay, so this completes the proof of sublemma 3. Okay, finally, let's look at the end of the proof of our theorem of lemma 2. So to complete the proof, we have to show that we have this condition. Delta C minus C tensor 1 belongs to this ideal. This is quite explicit. So we apply H tensor omega to delta C minus C tensor 1 star times delta C minus C tensor 1. So let's write this down explicitly. We have 4 summands here. H tensor omega applied to delta applied to C star C. This is the first summand, and here we use the fact that delta is a star homomorphism. The second summand is minus H tensor omega applied to C star tensor 1 delta C. The third summand is H tensor omega applied to delta C times C tensor 1 times, oh sorry, this is not correct, delta C star times C tensor 1. And the last summand is H tensor omega applied to C star C tensor 1. Okay, so this is what we want. We want to show that this is 0. Well, let's denote this summoned by alpha 1. This will be alpha 2. This will be alpha 3. And this is alpha 4. So let's first calculate alpha 4. Alpha 4 is, what is this? This is nothing but H applied to C star C. Because omega was assumed to be a state. What is now alpha 1? Alpha 1 is, well, this is the convolution of H and omega applied to delta of C star, applied to C star C. By assumption, well, our assumption was that H convolved with omega is H. So this is just H applied to C star C, and we see that alpha 1 equals alpha 4. Alpha 1 equals alpha 4. Let's now look at alpha 2. Alpha 2 is H tensor omega applied to C star tensor 1 delta C. So what's this? This is, we decompose this as usual by H and 1 tensor omega applied to C star tensor 1 delta C. And again, use the fact that 1 tensor omega is a left A modulo homomorphism. So this is H applied to C star multiplied by 1 tensor omega applied to delta C. Okay, and we now apply once again sublemma 1. Where is it? Oh, it's not here. Oh, here it is. This is sublemma 1, but now we read it from right to left. So we replace 1 tensor omega applied to delta C. Oh, where is it? No, this is not correct. Oh my God, this is an obvious, there is an obvious typo here. We cannot imply, well, let's look once again at sublemma 1. Where's the typo? The typo is that this makes no sense. because this is an element in A, and this is a functional on A tensor A. Of course, the correct form is like this, delta B and delta C. Sorry about that. And this is exactly the form which were used somewhere earlier. Well, otherwise the formula makes no sense. Of course, we can apply this functional and this functional only to elements in the tensor product. So we must have delta B and delta C here. Well, so we apply sublemma 1. Look here. In this place, why didn't you stop me? In this place, of course, we applied sublemma 1 in the new form, in this form, delta C. look, delta B, delta C. Now I hope everything is correct. Okay, I'm sorry about this typo. But now we apply sublemma 1 again. And we see that this is H applied to C star. And this is, we replace this by 1 tensor omega convolved with H applied to delta B. But what is omega convolved with H? This is omega by assumption. This is omega. So this is, as a result, this is H applied to C times 1 tensor omega delta B. Oh, sorry, of course not omega. This is H, sorry. Omega convolved with H is H. So this is H. And this is exactly C. This is exactly our element C, just by the definition of C. So as a result, we get H applied to C star C, and this is nothing but alpha 4. So we conclude that alpha 2 also equals alpha 4. The final step is to look at alpha 3. Now, actually, what's the difference between alpha 3 and alpha 2? So these two elements, this one and this one, are adjoined to each other. So they are adjoined to each other. And this is a positive functional. We know that a positive functional is Hermitian. That is, it preserves the involution. And so alpha 3 is alpha 2 complex conjugate, alpha 2 bar. But we already know that alpha 2 equals alpha 4. So this is alpha 4 bar. But alpha 4 is clearly a positive number, a non-negative number. In particular, it is real. So it is equal to alpha 4. So and in summary, we see that all four numbers, alpha 1, alpha 2, alpha 3, and alpha 4, are the same. And so the whole expression is 0. And as a result, we deduce that this element belongs to L to the respective ideal. Oh, thank you. Plus alpha 4. So delta C minus C tensor 1 sits in L H tensor omega. So now, applying first sublemma 3 and then sublemma 2, we deduce that sublemma 3 and 2, we deduce that nu satisfies our relation. And this completes the proof. Okay, so of course, a trivial example of Haar state is the integration with respect to a normalized Haar measure. If G is a compact group and mu is the normalized Haar measure, then the following functional is a Haar state. So this is the Haar state on C of G. Another example, example 2, and an exercise at the same time. We take a discrete, in some sense, example 2 is dual to example 1. We take a discrete group, G is a discrete group, and take the reduced group C star algebra of G. So we know that this is a compact quantum group in a natural way. And I claim, this is an exercise, that the Haar state the higher state on this algebra is given by the following formula. H of A, we apply A, which is an operator on the little L2 space, to the delta function at the identity and take the inner product with the same function. Okay, so our final goal for this course is to discuss the basics of the co-representation theory for compact quantum groups. Co-representations of compact quantum groups. So the co-representation theory of compact quantum groups is a natural quantum analog of representation theory of compact topological groups. It turns out that almost all essential results in the representation theory of compact groups have natural quantum analogs. Unfortunately, we don't have time to discuss all of them. In particular, we'll have to skip completely the famous Peter-Weil theory, which deals with unitary, in general, infinite dimensional unitary representations of compact groups, and tells us in particular that every unitary representation of a compact topological group is a Hilbert direct sum of finite dimensional irreducibles, which implies in particular that every irreducible representation of a compact group is automatically finite dimensional. This result also has a natural extension to compact quantum groups, but unfortunately its proof involves infinite dimensional co-representations, and the theory of infinite dimensional co-representations involves some non-trivial material from the C-star algebra theory. Namely, it involves Hilbert C-star modules and multiplier algebras. And unfortunately, we don't have time to discuss this material. So we'll restrict to finite dimensional co-representations, which is also quite an interesting special case. Well, first of all, let's recall some notation related to representations of compact groups. So first of all, if we have a finite dimensional vector space, E, well, by default, we always equipped E with the standard topology given by any norm. So the standard topology on E is the topology determined by any norm. It's a standard result that all norms on the finite dimensional space are equivalent, so we take any norm and generate a respective topology. If we have two finite dimensional vector spaces, E and F, let's denote by L of F the space of all linear maps from E to F. So it is also finite dimensional. So it has the respective standard topology. L of E is the set of all linear operators on E, which is also finite dimensional. And it contains the set of all invertible operators on E, GL of E. Invertible operators on E. And it's easy to see that GL of E is a topological group for the standard topology. That is, the group operation is continuous, and the inversion is also continuous. If now G is an arbitrary topological group, then by definition, a representation of G on E, where E is a finite dimensional vector space, is a continuous group homomorphism, say pi, from G to GL of E. Where GL of E is equipped with the standard topology. In the infinite dimensional case, the definition is a little bit more delicate, because we may introduce different topologies on GL of E, if E is an arbitrary Banach space. The standard choice is to take the strong operator topology. If we equip GL of E with the operator norm topology, then the respective definition is reasonable, but it leads to a very narrow class of representations. It turns out that most interesting examples of infinite dimensional representations are not continuous for the operator norm topology, but they are continuous for the strong operator topology. Anyway, in the finite dimensional setting, all reasonable topologies on GL of E agree, and we simply take the standard topology generated by the operator norm. Well, let's now look at a quantum analog of this notion. Что? The strong operator topology is the topology of pointwise convergence. But in the setting of finite dimensional spaces, we don't need this topology explicitly, because anyway, it agrees with the standard topology. Да. Okay, so let's now, to define the quantum analog of this notion, let's introduce some notation. Here we have two unital algebras, A and B. Unital algebras. Let's consider the following two inclusions. I12, which takes B tensor A to B tensor A, and I13, which acts between the same spaces. So these maps are given by the following formulas. It takes every elementary tensor B tensor A to B tensor A tensor 1. And similarly, I13 takes B tensor A to B tensor 1 tensor A. And for every element U in the tensor product of B and A, let's denote by U12 the image of U under I12. And similarly, we consider an element U13, I13 of U. So these are two elements of this triple tensor product. So this is the so-called leg numbering notation, which is quite common in the theory of compact quantum groups. So the indices 1, 3, and 1, 2 are the legs of U. We now give the following definition. Suppose that A is a compact quantum group, and E is a finite dimensional vector space. By definition, a co-representation of A on E is an invertible element, U, in the tensor product of L of E and A. So simply we take here the algebraic tensor product of two algebras, L of E and A, which satisfies the following condition. 1 tensor delta applied to U equals U12 times U13. So this is an equality in the triple tensor product of L of E tensor A, and here we take the spatial tensor product of A by itself. Well, indeed, the left-hand side sits exactly in this space, and the right-hand side sits in the smaller subspace, namely in the algebraic tensor product of L of E, A, and A. But anyway, both elements can be considered as elements of this space, so they are assumed to be the same. So let's now understand, so in conclusion of today's lecture, let's try to understand where this relation comes from. Of course, it comes from the commutative case. So let A be the algebra of continuous functions on a compact topological group. G is a compact group. Then L of E tensor A, this is the space where U sits, this element sits in here, is naturally identified with the space of all continuous functions on G with values in L of E. So our element U becomes a continuous function from G to L of E. Moreover, it takes G to GL of E because U is assumed to be invertible. This is a continuous function. Now, what is this space, this triple tensor product, L of E tensor A tensor A? Well, this is nothing but the space of all continuous functions of two variables, that is, continuous functions on G cross G with values in L of E. Then, what is 1 tensor delta applied to U? This is a function of two variables, and it's easy to see that this function evaluated at x and y is nothing but U applied to xy. What is U12? U12 applied to x and y. So we look here, and we see that this is nothing but U of x. And finally, U13 of x and y equals U of y. So we see that our relation, which appears in the definition of a co-representation, 1 tensor delta U equals U12, U13. So this happens if and only if U of xy equals U of x, U of y for every x and y in G. That is, this means that U is nothing but a continuous representation of G. So we deduce that in the commutative case, that is, in the case of where our compact quantum group is just the algebra of continuous functions on a compact topological group, co-representations of this algebra of this compact quantum group bijectively correspond to representations of G. So this is the main motivation for our definition. Okay, so that's all for today. At the next lecture, we discuss intertwining maps between co-representations. Of course, they correspond to intertwining maps between representations. We'll discuss a relation between co-representations of A and representations of the dual algebra, the convolution algebra A star. And we discuss invariant subspaces and the notion of an irreducible co-representation. of an irreducible co-representation.